Hello, in this video we're going to take a look at some evaluations of Taylor series, in particular Maclaurin series. We'll see it in the context of the so-called binomial formula or binomial expansion, and we'll see how Taylor-Maclaurin series can help us in finding the sum of a series. For our first problem, let's consider this. G of x is given by 1 minus 2x squared, all raised to the 3/2 power. We'll find the value of the sixth derivative of g at 0. Now we're going to do this by finding the Maclaurin series for g of x. We know the Maclaurin series has coefficients that are expressed in terms of various derivatives of g at 0. And we'll then relate the coefficient of x to the sixth in that expansion to the value of the sixth derivative at 0. Now we're going to use the binomial series to do this. The binomial series is the Maclaurin series for an expression of the form 1 plus x to the m. So let's let f of x equal 1 plus x to the m. Now when m is a constant like 1/2 or minus 1/2, you'll see these things occur quite often. But what we say here will hold for any exponent up there, any real number, square root of 2, pi, a positive integer, whatever. So in section 10.10, they look at the Maclaurin series for 1 plus 1 over x to the mth. And it's given as you see below here. And we know that in a Maclaurin series, the coefficient is various derivatives of the function at 0 and then divided by factorials. So for example, if we look at the x squared coefficient here, that turns out to be the second derivative of f at 0 divided by 2 factorial. So it's not hard to see that that second derivative at 0 is given by m times m minus 1. Here you see the term that arises from the third derivative, f triple prime of 0 over 3 factorial, etc. Now, as the derivatives, as you move out in the series and the derivatives get longer and longer, this coefficient becomes harder and harder to write. So mathematicians have devised some new notation. We see that for example, we're going to use this notation called m over 2 to denote this quantity, m times m minus 1 over 2 factorial, and the notation m over 3 in big parentheses denotes m times m minus 1 minus 2 over 3 factorial, etc. And of course, m0 evidently turns out to be 1. These are called binomial coefficients. So the binomial coefficient m over k, often read m choose k, is notation just to save some writing, so we don't have to get involved in writing long expressions for these coefficients as we talked about earlier. So the m choose k is defined as follows. See in this line, m choose k is given by, we simply start multiplying numbers in the top, starting with m and going down in steps of 1. m minus 1, m minus 2, etc., until we get to m minus the number k minus 1. This gives us k terms on the top, then we divide that by k factorial. Okay. And this is, in fact, this upper part is in this above expansion is the numerator is the nth derivative of f at 0. Okay. So this gives us a simple, easy way to write the coefficients in the binomial series. This expansion, by the way, is called the binomial series or the binomial expansion. Of course, it is a Maclaurin series. It's called the binomial expansion because 1 plus x is a binomial, and we are expanding it when we raise it to a power. So let's compute a couple of these coefficients just for practice. Remember, you start, whatever the number is up here, that starts the chain of factors in the top. And how many factors do you have? Well, that's what the bottom number tells you, k. So for example, if we have to compute m choose 2, m over 2, we know we're going to have 2 factors in the top. And whatever those factors, they start at m and they end at m minus the k, which is 2 minus 1. And of course, there's going to be just two factors. And so this gives us just m times m minus 1 over 2. And for something a little more complicated, we could have minus 3/4 choose 4, as we see here. And again, we're going to have 4 terms in the top. And we get those by starting with 3/4, then 3/4 minus 1, 3/4 minus 2, 3/4 minus 3, etc. Just keep up that chain of multiplication so you have 4 terms divided by 4 factorial. And there's the result of the arithmetic. So back to our problem, we're dealing with g of x equals 1 minus 2x squared to the 3/2. We're going to start by finding the Maclaurin series for this expression. We're going to do this by substituting minus 2x squared in for x in the binomial series. So if we look at the binomial term, 1 plus x to the 3/2, we see that's very much like g, except the x has been replaced by minus 2x squared. So you're going to hear the word template a lot. I think of formulas like this as templates. Which means this: if you replace x by anything else you like consistently on both sides, you'll still have a true formula. So in this case, we're going to replace all the x's we see by minus 2x squared. And so that gives us the following: g of x, or 1 minus 2x squared to the 3/2. Its binomial series looks like this: just 3/2 choose 0, 3/2 choose 1, etc. And you can match up each term with the term up here and see how those things stack up. Okay. Now, the second step, we just did a little of the algebra here. We have things like minus 2x squared cubed. If you expand that, you get the minus 2 cubed is minus 8, and the x squared cubed becomes x to the 6th. So we've done that just to clean up this series a little bit. And there's a pretty obvious pattern here. We see the binomial coefficients in their usual order, and then increasing powers of 2. 2 to the 0, 2 to the 1st, 2 to the 2nd, etc. as we go out here, and then alternating signs. So this is the Maclaurin series for g of x equals 1 minus 2x squared to the 3/2. Notice we didn't have to compute all the derivatives to get those coefficients. We used a known series, the binomial series, and just made a substitution. Now we're pretty close to answering our question about the 6th derivative, and that's this. So as we just mentioned, there's another way to get the Maclaurin series for a function like g of x, and that's just by grinding out derivatives at 0, dividing by factorials, and forming the coefficients. So that's what you see here. We haven't actually done that calculation, but for any function that has a Maclaurin series, that is the Taylor series expanded at about 0, this is how you would get it. Now, one of the great things about these series is that a function has exactly one Maclaurin series. So even if two people get at a series about 0 for a function by different means, those series are both the Maclaurin series, and so they have to be identical. So because of that, we're going to take the two ways we know to talk about Maclaurin series. There is this way, which is kind of the way Maclaurin series was defined. And then we have this other expression we just derived. We also saw g of x looks like this. So again, these are both Maclaurin series. They both express g of x as a power series about 0. Now, because the Maclaurin series is unique, the coefficients of x have to match up. Should note down here, now our g of x that we derived on the previous slide had only even powers of x in it. It had a constant term, x squared, and x to the 4th term, etc., and x to the 6th. Notice we have filled in the missing powers with coefficients of 0. There were no odd powers in that work we did on the previous slide. So because of the uniqueness of Maclaurin series, the fact there's only one, this tells us that if we look at a power of x like the 6th power, those two things must be the same. In other words, the coefficients in any two Maclaurin expressions have to be the same. So we're going to use that to come up with the derivative, the value of the sixth derivative of g at 0. So in fact, what we do here is we pull down those two coefficients we had circled earlier. That's these two. And because the Maclaurin series is unique, I keep repeating that, but it's a very important idea, we know that those two expressions must be equal. And so now I can get at g, the sixth derivative of g at 0, by just multiplying both sides by 6 factorial after canceling out the x to the 6th. So we get this formula for the sixth derivative. And if I look at the binomial coefficient, 3/2, choose 3, you can do the arithmetic. That comes out to be minus 1/16. And the product then gives us 360 for the value of this derivative. So computing this sixth derivative of this term by hand would have taken quite a long time. Lots of applications of the product rule and chain rule would have gotten very long. And then at the end, we have to put in 0, do the calculation. Here was a very quick kind of shorthand way by using a known series, the binomial series, to get a Maclaurin series for our function g, and then we can equate it to the generic Maclaurin series formula and came up with that sixth derivative with really very little trouble. Okay, let's look at a different kind of example next. Let's find the sum of this infinite series. Summation k runs from 0 to infinity minus 1 to the k, 1 over 2k plus 1 times 3 to the k times square root of 3. And if we expand that, we get these terms. K equals 0, k equals 1, etc. Okay. Now, we've done some work with series in the past and looked at some sums of series. So far in our work, we've generally found if we have to find the sum of a series, we hope it's either a geometric series or a telescoping series. Those are the main kind of series we've been able to sum so far. But it turns out that many series, and this is the one above is one such example, actually arise from known power series. So if you can link this series with a known power series, you can actually do the evaluation by understanding what the power series must equal for a particular value of x. Now, the way we make this work is this. With these terms in the denominator here, these 3, 5, 7, etc., it's unlikely this is a geometric series. And with the 3 to the k terms, we see, this thing, unlikely that it's telescoping. Those aren't usually the things that occur in telescoping and geometric series. So what we're going to do is we're going to take a look at the list of frequently used Taylor series on page 620 of the book. And we're going to find a series that kind of looks a little bit like this and see if we can't work the two series together to actually resolve the sum we want. So I suggest you pause the video at this point and look at the table on page 620. What power series do you think best matches this series? Okay. So I'll assume you've paused, so I won't. So let's move on. So it turns out that because of these odd numbers, there's you can think of a 1 here, and the 3, and the 5, and the 7, etc. in the denominators. And the fact there's no factorials, it's not too hard to narrow this down to think, well, if anything, it looks a little like the arctangent or inverse tangent series. So this is the one you see on page 620. It looks like this. I think it's the bottom of those things. And it's just really pretty simple. Somebody start to write it out. Various odd powers of x. The series alternates, plus minus 1. And these denominators are 1, 3, 5, 7, 9. And those match up well with the 1, 3, 5, 7, etc. we see in these denominators. So we're going to hope that the series we have to evaluate is equal to this series for some particular value of x. Now, if we line these two series up one over the other, here is the one we're trying to determine, and here is the inverse tangent series. So we've kind of lined them up. And if this series really is an inverse tangent, it's very likely that the x has been replaced by 1 over root 3. So the x, the inverse tangent series. And so we're going to check that out, see if this works out. So we're going to work with the given series and show that it actually can look like this series with the x replaced by 1 over root 3. We're going to make use of the elementary fact that 3 is equal to root 3 squared. And so let's see how this works out. So down here, again, here's the series we're trying to work with. And we've written the 3 as root 3 squared down here. So the 3 to the k has become root 3 squared to the k. And then if we bring all the powers of root 3 together, we find this is root 3 to the power 2k plus 1. And then this root 3 power in the denominator can be thought of as a 1 over root 3 to the power 2k plus 1 in the numerator. And if you match this series up with the one here, you can see this looks like evidently just inverse tangent of 1 over root 3. In other words, the x has been replaced by 1 over root 3 in that inverse tangent series. Okay. So once we know that, the evaluation becomes pretty easy. It's just a matter of evaluating an inverse tangent or arctangent at a point. So we have kind of settled on the fact that the series we're trying to sum is really just the series for the arctangent with x replaced by 1 over root 3, or inverse tangent of 1 over root 3. And so the question, what angle has tangent of 1 over root 3? Well, that's pi over 6. And so the sum of this series turns out to be pi over 6. Okay, so what's important in this video? We've seen in several videos now that substitution in the known series is a very, very powerful tool. We used that twice in this video. For the one case, we had the binomial expansion for 1 plus x to the 3 halves. We replaced x by minus 2x squared to get the expansion for the function g of x we were looking at earlier. In the second example, we replaced x by 1 over root 3 in the arctangent series, the inverse tangent series, and that helped us determine the sum of the infinite series. So this idea of substitution is very important. Look for it. You'll use it a lot. And it's a very easy way to relate series you have to power series. We also use a very important fact that a function f of x has only one Maclaurin series. Okay? This means if you have two such series and you know they're both Maclaurin series for a function, then the two series must be identical. And what that means is that the coefficients of x to the k must be the same in the two series. Okay. And in fact, more generally, if you have a function f of x and a value c, the function has exactly one Taylor series centered at the point C. So in this way, if you have two different expansions for a function, both in powers of x minus c, they are both Taylor series, and hence they must be identical. And again, you can do this coefficient matching. And then finally, it's important to know, you should really memorize most of those series on the table on page 620 of your book. Oftentimes work with series is just a matter of recognizing a series that you are familiar with and then working that familiar series into the form of the one you're trying to cope with. And that was, of course, the idea in the second example. So have fun practicing these, and thanks for listening. Goodbye.